Hello everyone, I'm Mei from the University of Singapore. I will share our recent work on the anthropogenic heat dispersion with the residential area. Previous studies show that anthropogenic heat can warm our street air significantly. For tropical cities, such as warming effect should be controlled to guarantee the healthy outdoor environment. The two questions remain unanswered: how much the air temperature will rise in a real urban configuration, and how the building typology can affect the temperature rising. In order to answer these questions, we conducted a safety simulation in a residential area in Singapore. The residential area we choose contains three types of HDB buildings. The HDB is a public house program in Singapore. The energy consumption data is used as a boundary condition for the safety model. The air conditioner condensers are considered as emission point of the residential air anthropogenic heat. We conducted a field survey to find out the number and location of these condensers. The locations of this condenser are marked as red in these slides. The anthropogenic heat emission is calculated from the electricity consumption. We assumed all the electricity are used for the air conditioning. We also checked the cooling load and found the majority of the electricity is truly on air conditioning in Singapore. The anthropogenic heat from condenser consists of two parts. The first one is the electricity consumption, which is used to power the compressor, and the second part is the heat transport from the indoor to the outdoor through the heat engine cycle. We choose a wind tunnel experiment with buoyancy effect to validate our safety model. The comparison in this slide shows the safety model could accurately predict both the wind and air temperature distribution. The inflow velocity reproduces the turbulent structure of the atmospheric boundary layer. Four dominant wind directions of Singapore are selected for the simulation. The annual wind speed and lowest wind speed are used for the simulation. This slide shows the temperature at the surface under the annual wind condition. The inside layer represents the temperature increment of 1 degree, and the outside layer is 0.5 degree. The hottest zone was found at the wake region of the roof level. The downward motion induced by the wind-driven flow and the annual wind condition is the main reason for the pedestrian level air warming. This slide shows the low wind condition. The ambient wind is very weak, and the buoyancy dominates the flow below the roof level. The buoyancy effect transports the warm air upwardly, causing weak influence on the pedestrian level. So the pedestrian air temperature could be low at the low wind condition. The air temperature increment at the pedestrian level is plotted in these slides. There are three different types of buildings in the high-density area. The Pentagonal area buildings are the new type HDB with a uniform height of 150 meters. The Everton Park buildings are old type and the low-rise HDBs with a height about 4 meters. The buildings are lined up continuously and closely spaced, forming a typical street canyon. The cantonment neighborhood are formed by tall buildings with a height of 74 meters. The buildings are sparsely spaced, forming wide wind paths between the buildings. The pedestrian level air temperature elevation is highest at the Everton Park, which is about 1 degree between the buildings. Due to the vertex structure, the air exchange rate in the street canyon is low. The heat release at the cantonment buildings only heat up narrow zones close to the heat source, indicating a good outdoor ventilation performance. The temperature fluctuation could also impose significant impact on the pedestrian level thermal comfort. Therefore, the temperature time series in the steady-state period was plotted. The test points are located at the pedestrian level in the Everton Park, where the temperature rising is the highest. The peak value of P4 are about 1.4 degree. Under the low wind condition, which is about 0.4 higher than the average value. Under the annual condition, the peak value of P4 is about 1.6 degree, where the average value is around 1.2 degree. The time span of the temperature fluctuation peaks are in magnitude of 10 to 100 seconds, which may also influence the pedestrian level thermal comfort. Generally, the fluctuation intensity is higher under the annual wind condition. The intense fluctuation in the annual wind scenario indicate that turbulent fluctuation is partially responsible for the street air warming. Under the low wind condition, the vertex flow structure is changed by the buoyancy force, resulting in stagnation. The fluctuation intensity also depends on the location. For example, the temperature fluctuation at the P6 is very low under the low wind condition, indicating an L stagnation at that point. However, the other point does not show such stagnation under the low wind condition. The main conclusion of this study include, firstly, the building typology, wind speed, and energy consumption rate are the main factors for the temperature distribution at pedestrian level. Secondly, the maximum temperature increment of 1 degree at all time HDB, which is formed by closely spaced building row. Thirdly, compared to the low wind speed condition, the high wind speed causes higher temperature increment at the pedestrian level. Lastly, the highest fluctuation intensity is estimated of magnitude of 0.4 degree, which may also influence the pedestrian level thermal comfort. That's all. Thank you for your attention.